have our discussion in, for example, if we have some experimental situation with us, you can put your camera up now. Okay, is my voice is clearly audible?
Yes, sir.
Yes, sir.
Okay, some of the students from other sections are telling about the solution of our first quiz. Actually, the thing is that the questions were so easy and elementary that it doesn't require any solution. Okay, your answer is given there. Try to verify with your solution. Okay, if you feel that something is wrong with it, then let me know. And roll number 104 of section 1, who got 9 out of 10. Probably one question was there, and still it is my under review. Okay, I can you maybe get full mark. So you can consult with them if you have consult with him if you have your problem. But your engagement is necessary. I usually do not give any blanket suggestion to anybody. Okay, you try your best, then let me know that something wrong is there. Now, in general, what we do in many of our practical purposes, we perform experiment or we observe some data for a statistical measurement, or we collect some samples in many of our practical purposes and try to analyze the data with the help of some statistical measurement. This thing is very important in many perspectives. In our engineering particularly, if you want to have some model. Model means what? Usually a mathematical model, okay? That mathematical model can be a predictive one. That means a completely certain mathematical model that is actually not available in any of our practical measurement. What you need to do after observing a practical scenario, we try to fit that scenario to a mathematical model. And that mathematical model later then represent that scenario so that by using that mathematical model, we can proceed our further discussion, further step of analysis or something like this. All these things actually belong to the category of curve fitting. Let us start with a very simple example that in your student life, you have been asked to verify Ohm's law. Did you verify Ohm's law in your laboratory?
Yes, sir.
Okay. Does it follow this curve exactly?
No, sir.
Or you can write this thing in this way, I is equal to B divided by R or something like this. Then if you want to plot, for example, this graph in our graph paper, we considering that B is in this axis and I is in this axis. Theoretically, this curve should go through the origin and it is a straight line, isn't it?
Yes, sir.
Did you find that straight line in your laboratory measurement?
No, sir.
Then what change was there?
So there are some deviations from the linear region.
That deviation is what type of deviation it was?
The points are somewhat upper and lower or lower than the linear curve.
That means you may have some point there measured in this way. That means
Yes, sir.
coming in this way, or in other cases, some measurements might have some uncertainty.
Points are very scattered, sir.
Okay, and it is very scattered or something like okay. But if it is scattered, for example, in this fashion, but if we can plot it in a graph paper with that scattered value, at least we can estimate a trend, isn't it?
Yes, sir.
Although it is not a straight line, but we can estimate a trend that whether it visually resembles a straight line behavior or some other behavior. Or if you want to measure the current flowing through a diode with respect to voltage, you will see that theoretically it has this nature, okay? But you practically observe that your current is something like this, okay? Isn't it?
Yes, sir.
All these measurements are even if you have your for example in a social science, for example, say in a certain region you want to measure for example or in economics, for example, say you want to investigate how the share price of a particular company is increasing with respect to time, then that will have some data, something like this, isn't it? You can have a trend there, how the things are going. In all the cases, actually, if we have our measured data scattered, then some data might fall, for example, due to the erroneous measurement, you may have a data coming here. If your
Sir, are you talking? Can't hear you, sir.
I'm sorry that probably I could not finish what we are discussing about. So the thing is that what we have discussed earlier, that if we have an experimental model, that experimental observation actually needs to be modeled by using some mathematical functions, then we need to use something, some mathematical technique, so that that mathematical function will represent our data correctly, okay? In your book, those things are there described. You try to have a look, but I will be considering this whiteboard to discuss this issue, okay? If you have your question, then you can ask me. Consider that we have a data that we're representing this variable y and x. Okay, it can be voltage current, it can be other factors, whatever it may be in our real life. If we have this measured value, for example, something like this, and although we can observe that this scattered data is following a trend, but in order to find that trend line, we have to devise some mathematical ways to represent this data mathematically. This sometimes called curve fitting, or sometimes called least square regression. Curve fitting means you have to derive or develop a curve so that that curve will best fit the what you call the measured observation. Now we are using a term best fit. Best fit means what? How to measure that what you call bestness, okay? That it will fit best. Okay, someone can draw a line in this way, for example, and this straight line can have in equation relationship, say a0 plus a1 x. But if you want to find the value of a1 and a1 for a particular, you can, if someone can say that we can use the value of x1, the corresponding value is y1, then we can put this value there, that is y1 is equal to a0 plus a1 into x1. Then we can find another value there with x2, then find the corresponding value of y2. Then your y2 would be equal to a0 plus a1 into x2. In this way, we can form two equations to solve for a1 and a0 and a1, isn't it? So do you think that that technique will be good for predicting the relationship between x and y?
No, sir.
Why not?
Sir, because
Because
we're
if we have, yes, because if we have only 2 points, then we can do that. But if you have a multiple points there, we cannot do that. The reason is that this will not be a good fit for this region because we have some differences at each point. That differences should be counted in such a way that we have to find the value of A0 and A1 so that differences will be minimum, okay? Now the condition is that how to minimize this difference. This is the big question, okay? The reason is that at each point, for example, if we want to calculate the error, that error E at ith point would be equal to our original value measured yi minus we are predicting the value by A0 and A1 with xi, isn't it?
Yes, sir.
And that particular difference is sometimes called residue. That residue of the error is different at different points. In some cases, it can be positive. In other cases, it can be negative. So if someone will just try to devise a way that we want to set this error criteria, sum of EI, if your data is from I equal to 1 to n, we have to make this sum and use this sum and make this sum minimum to find the value of A0 and A1. But that criteria is not actually viable. The reason is that you see that sometimes this sum can have 0 value. That will not tell you that we have our 0 error. The reason is of the 0 is why? The reason is some error are positive, residue are positive, some residue are negative. If this is the case, then what will happen? This will be an ambiguous something, okay? Other can say that we can calculate the absolute value of error. That absolute value of error will also not be a viable criteria. Other criteria is also there. They are discussed in a book. Okay, all these criteria actually prove to be not useful for this purpose. What we usually do in the curve fitting that we calculate a square of sum of errors in this way. That I equal to 1 to n, and that sum is yi minus a0 minus a1 into xi squared. You see that if we square this quantity and this is real, then is there any possibility to that SR become 0 due to
No,
the
sir.
negative cancellation?
No, sir.
Why? The reason is because this is the square of a real number. A square of real number is always
Positive.
always positive. Okay. Now, if this is your error, then what we need to do, we have to find the way with the help of this error, we have to find the value of A0 and A1 so that error SR, which is the function of A0 and A1 actually will be minimum. Okay. That means we have to minimize this function. So how we usually used to minimize it, you know that when a function is minimum or maximum, the slope of your function at that particular point would be flat, isn't it? For example, if we keep one variable constant and try to plot SR with the other variable, if we will be going in this way, then what will happen at this point, you see that your curve is flat. Then is it not the minimum point?
Yes, sir.
Yes, sir.
Even it can be a maximum point, but in order to test it, you have to calculate the next derivative. If it is negative, it is minimum, maximum, and if it is positive, it is minimum. Okay, you know this thing from a very basic algebra in the earlier case. Okay, that is what the technique will be employing it to find the value of A0 and 1. The reason is that if we have a model to be developed for this particular data, A0 plus A1 into X, here the unknown is actually A0 and A1. We have to choose the unknown or determine the unknown in such a way that the error that we are obtaining at each point and squaring the error sum and make this sum of square of errors minimum. This algorithm is called a least square error. Okay. Least means minimum squaring error. Okay, that means we are our calculation procedure is something like this. We have to calculate the error first, then we have to square them. Least actually least sum should be there. Okay, sum square error. Then we square it, then we sum it, then we make it minimum. Okay, in this way we can proceed in determining the value of A0 and A1. Now tell me, if we differentiate equation, this equation, say this equation 1, that is sometimes called residual error, residual square of residual equation. Then you see that S is the function of A0 and A1. Then if we want to find the optimum value of A0 and A1, what you need to do first, you have to differentiate partial derivative, of course. The reason is that two functions are involved there, A0, A1. And you put your A0, A1 into D A0 equal to 0, then you will have another one equation. Another equation would be DSR A0, A1 with respect to DA1, then this will give you another equation. Okay, can you find the first equation? Is not it equal to -2 into sum n equal to 1 to n yi I equal to yi minus A0 minus A1 xi. Is it okay? Because your original,
From which one this -2 came, sir? If you would clear.
you are differentiating with respect to A0, okay? And that A0 coefficient has a negative sign there. Then if you differentiate -1, because you know the how to differentiate, a square term was there because of this square, A2 is there, okay? And next you have to differentiate the inner derivative, inner function. If you differentiate the inner function, this is 0, this is also 0, then d minus A0 by d A0 equal to what? Is it not -1?
Yes, sir.
That is what the thing, very basic level, intermediate level derivative, okay? And second term would be equal to -2 sum I equal to 1 to n. You got the point, because your function is yi minus A0 minus A1 xi squared, isn't it? If you want
Yes.
to take the derivative of this function with respect to A1, you put this function is equal to say y, capital Y. Then that will be equal to 2 into y, isn't it?
Yes, sir.
Then you have to multiply it with d divided by d1, a1 with respect to yi minus minus A0 minus A1 into xi, isn't it? And that is equal to what? Minus 2y into -1 is plus 2y into -1 is equal to -2 into y. That y is the sum function. This is your y. Is that okay?
Yes, sir.
Yes, sir.
Now, if you want to put find the second thing, then what will be the second derivative?
-2 xi into the same thing.
-2 into I equal to 1 to n yi minus A0 minus A1 into xi. That xi should be within the sum. Is it okay?
Yes,
Yes,
sir.
And how many equations now we have then?
2.
Okay, fine. Then your first equation can be put into this form, that sum I equal to 1 to n yi minus sum I equal to 1 to n A0 minus sum I equal to 1 to n what?
AIXI?
A1 xi equal to 0, isn't it?
Yes, sir.
Yes, sir.
And can you just out of these three terms, which is known to you? This
The middle term?
Why the middle one? Because your A0 and A1 are unknown to you. How can you say that this thing is known to you? Only the known term is your yi, isn't it? Sum of
Oh, all right.
yi. Because your observed data will be with you, isn't it?
Right, sir.
So if your observed data is with you, then you can easily sum this up. You can put, for example, this sum here in the right hand side. Okay, then this would be equal to sum I equal to 1 to n yi, isn't it?
Yes, sir.
Yes, sir.
And your first equation can be replaced as, because a is constant, you can put your a there. Then this sum equal to 1. Is it not equal to n? So this should be equal to what then? A0 into n, isn't it? Isn't
Yes,
it?
sir.
Yes, sir.
Then in this case, you can put your a out of the sum. A1 out of sum, you can, for example, put your a out of the sum. Then here, this is your sum and this is your A1. Okay, this is your first equation, okay? Then in the same way, can you arrange your second equation? In the second equation, which term will be known to you?
Yi again.
Yes, sir. Why?
Yi into xi, because xi is there.
Right.
Your xi and yi will be known to you. This is known to you, okay? Then another term with respect to xi would be equal to what? This is would be equal to A0 into sum I equal to 1 to n xi, isn't it?
Yes, sir.
Minus one and
Y minus is there because a minus was there earlier and we are putting
Oh,
the
okay.
sign in the other side.
Oh, sure.
Then,
Yes, sir.
then this would be equal to sum I equal to 1 to n. This is for that term. That means a squared I squared into a1, isn't it?
Yes, sir.
Now tell me, with the help of this minimum criteria that we obtain, you are obtaining two equations there. In these two equations, how many unknowns you have?
Sir, 2.
These two unknowns, okay? Okay, in this connection, I want to ask you one question, okay? Have you heard about Fourier series earlier?
Yes, sir.
Yes, sir.
Okay, in your Fourier series, what have you done? Because similar type of technique has been used there in Fourier series also. What is the actual utility of Fourier series? Why we need it? Can you answer this question? That why we need Fourier series?
To decompose a signal to sinusoids and cosine waves.
To decompose a signal into sinusoid and cosinusoid. Fine. All types of signal can be decomposed
Sir, the
in Fourier
continuous
series. Actually, the thing is that it is an approximation technique. Okay, for example, say if you have a square wave, a periodic square wave, isn't it? With a period equal to say t. Is it not a periodic wave?
Yes, sir.
Yes, sir.
If it is periodic wave xt, what we are doing that we are saying that that periodic wave xt can be approximated as a function something like this. Okay, a pool of function is there, theoretically infinity n into cosine n omega 0 t plus bn sine n omega 0 t. Have you used this equation earlier? Wherein omega 0 is called the fundamental frequency that can be obtained from the original periodic wave. This is called fundamental angular frequency. Isn't it?
Yes, sir.
All
Yes.
other frequencies will be the integer multiple of fundamental frequency. Those are called harmonic frequencies. Now, what are the unknowns actually to be determined? Are not those things an and bn?
An and bn.
Then you have to calculate the value of an and bn such that the discrepancy between your original xt minus x approximated t, you make it a square and sum it and take the average value. That will give you an equation that particular function a error will be the function of an and bn only. Are not they? Like it, this square residue that we calculated. Then you have to take the derivative of E with respect to N, set it equal to 0. Take the derivative of E with respect to Bn, set it equal to 0. Then with that setting, you can obtain the value of An is equal to 2 divided by T integration minus T by 2 to T by 2 xt into cosine n omega 0 T dt, and your Bn would be equal to 2 by T minus T by 2 to T by 2 xt into sine n omega 0 T dt. I hope you derived this equation earlier in your mathematics course.
Yes, sir.
And that particular logic that we are obtaining here is also called least mean square error criterion that we are also using in our least square curve fitting. Okay. In this case, average value is not used, but as it is a time dependent function, so instantaneous value cannot be used there to calculate the error and BR. For this reason, we need to average the error within one period of your original wave that will give you this thing. Okay. So this is also a least square error curve fitting type technique. Okay. In this case, if you have, for example, other than a function xt given, if you are given some experimental observation that has some periodicity, then you can also fit those curves by using An and Bn in the form of a Fourier series. So this also belongs to our curve fitting technique. Okay, with this discussion, let us apply this thing with an example. I hope you have your calculator with you. Consider that you are obtaining, for example, a VI curve in your laboratory for a resistor. Okay, you are applying a voltage, say an element, you are applying a voltage, say 1 volt there, and obtaining a current, say 0.25 ampere, say, and you are increasing the volt 2, then your current is, say 0.35 ampere. You are obtaining a voltage 3, your current is, say, what do you call, say, point is, say it is 5 ampere, 0.5 ampere, okay. If voltage 4, say this point is equal to, say, 0.75 amperes. Now you see that if we plot, for example, this thing to a graph paper, it is a scattered plot, isn't it?
Yes, sir.
Yes.
And if we want to, for example, first, after having the data measurement plotted in a graph paper, you will be obtaining a scattered plot. That scattered plot will give you some idea about the nature of variation of your data point. Okay, and you can see that it is changing or increasing with the applied voltage, and it can take the shape of a straight line or something. If we plot this thing, you see that for 1 volt V, your current is, say, 0.25 ampere. Say this is what that point. And for 2 volts, say we are obtaining a current equal to 0.35 ampere. Say this is something like this. If we have a current 3 volt, then we are obtaining a current something like this. If we have a 4 volt, we are obtaining current something like this. You can easily see that your voltage is taking in the form of a straight line or something like this, isn't it?
Yes, sir.
Yes, sir.
If you want to plot a curve for each of the point that is touched, then you will see that that is not a best fit. You will find that it will have some point that will be completely undefinable. Those things are described at the beginning of the chapter. You try to read them out so that you will understand that how your curve fitting can be there. Okay, what we are discussing at the beginning, that we are using a linear curve fitting technique. Linear means we are approximating our scattered data by a linear equation in the form of a straight line. So in this case, what will happen? We do not know actually what will be the parameters of this straight line, but those parameters that is a straight line will be affected is equal to what? V is equal to, say, a constant A0 plus, say, a constant A1 into I. Is it reversed? Is it not reversed? Is it okay? The general form is y equal to A0 plus A1 x, isn't it?
Yes,
Yes,
sir.
Now you have to find the value of A1 and A0 that we have discussed earlier, okay? So in order to do that, you have to find that matrix A0 into N plus sum Xi into A1 is equal to sum Yi, isn't it?
Yes, sir.
And the other one was, can you remember this thing? A0 into sum of Xi, then sum of X square, sum of Xi into Yi. Is it okay? So your next equation will be equal to what? A0 into sum of Xi
Yeah.
plus A1
X
into
square.
sum of Xi square is equal to sum of Xi Yi, isn't it?
Yes, sir.
Okay, then can you find this thing? You have to calculate it. A0 n is n equal to 4. Okay, so your first equation is 4 into A0 plus second is sum into Xi. This is your X, this is your Y. What is the sum? 4, 3, 7, 10, isn't it? It is equal to 10 into A1, isn't it?
Yes, sir.
What is the sum of Y?
So
0.25
1.8.
plus 0.35 plus 0.5 plus 0.75
1.85, sir.
is equal to 1.85, okay? So in your last case, what is the value of thing this? This is equal to 10 A0, isn't it? Because sum of Xi equal to 10
Yes,
plus
sir.
if we square our X and sum, square and sum equal to what? If we square it 1,
30,
4,
sir.
9, 16 equal to 30.
Yes, sir.
Okay, then it will be equal to 30. 30 into A1 is equal to sum of Xi into Yi equal to what? 0.25 plus 0.7 plus 1.5
5.45,
plus 3. 5.45.
sir.
Okay, fine. If you have these two equations now with you, can you solve for A1 and A0?
Yes, sir.
Yes, sir.
What is the value of A1? Four, 10, 1.85, 10, 30, 4.45.
Sir, 0.05 is A0 and 0.165 is A1. Not sure if it's correct, but this is what's showing.
Sorry.
Sir, 0.05 is the value of A0, and 0.165 is A1.
How about others? All are sleeping?
No, sir, we're following, sir.
Or then can they calculate it? Your equations are 4, coefficients are 4, 10, 1.85. The next is 10, 30, 5.45. So your first solution is equal to what?
0.05.
First solution is A0 equal to 0.05 and your A1 equal to
0.165.
your A1 equal to 0.165. Is it okay?
Yes, sir.
Yes, sir.
Then your straight line equation VI characteristic that you are obtaining is equal to what? Your I is equal to 0.05 plus 0.165 into V, isn't it?
Yes,
Yes,
sir.
sir.
This is now, you can say that this is the exact relationship of your Ohm's law that you followed in your experiment, okay? Then at
Yes,
each
sir.
point, can you calculate the error? that how residue, you can just compare the goodness of your feed in this way. Okay. This is your I, this is your I predicted. Your I predicted can be calculated by using that equation. You can fill this term out.
Sir, and then we will find the difference.
You can find the difference individual point. Okay.
Okay,
Then
sir.
by using that difference, if you square them out and sum them, this is your square error SR. Then by using your statistical method that you obtained earlier, you can easily calculate the average value of your current, and you can easily check how your current is changing from the average value. Okay. That will also give you another statistics of closeness of your feed. Okay. Using these two values, another criteria usually we obtain, that is there in your text. I want to share the text with you, but where is it? Okay, let me open it up. Lots of people are there. When I am taking my class, they are phoning me because this university is actually, some people are there, they are not aware of the role of the teacher. Okay, I am the departmental head. They usually think that your departmental head is the only department managerial purpose. Okay, we are taking class. They do not have any idea about it. For this reason, while I am taking class, they are continuously phoning me. And not only that, a admission test is going on, most hazardous, something that we are doing this time. Every day some problems are there and people are continuously hunting me. I am getting actually mad. So at the beginning of the chapter, you have some statistical measurement. Okay, try to follow this thing because those things are there in your with you in your earlier courses, because you have your statistics courses you already attended, and also you have your RSP probably, isn't it? Random signal processing.
Yes, sir.
Then you know the many of the perspective of the statistical measure. Okay, even some of them is still not. I am not comfortable with those things. The reason is that I have not. I did not touch this thing for a long time. Okay. So this is your 17.1 that we have already discussed. Okay. The
Sir,
residual.
your screen is not visible, sir.
Oh. Now it is visible probably.
Yes, sir. It is clear now.
Okay. Then 17.3 we have already discussed. Okay. By using 7.17.3, we derive these equations. Okay, you have already with you. Okay, equation 17.4 to 17.6. Using this thing, we have already solved the equation for a particular small example, and you have a big example there. In example 17.1, you try to have a look. Okay. But few things that we need to consider about, we need a measurement just to estimate the goodness of the feed. This is there at 17.9. Please try to have a look. But this is important to note actually. The thing is that if you want to find the spread of data, we refer to a particular value, then you will see that in most of our practical measurement, that spread can be what you call represented by a curve, that bell-shaped curve. We call it normal distribution. I hope you have the idea about normal or Gaussian distribution in your earlier courses, isn't it?
Yes, sir.
Yes, your Gaussian distribution actually depend, because this is actually a probability curve with zero mean. Okay, in general, but in practice it will not have a zero mean. For this reason, we use a normalized normal curve. Okay, and you need a table of this normal curve to, otherwise you have to integrate it in order to calculate the area, because total area of this curve, normal curve, would be equal to 1, and usually it will have a zero mean. That means it is centered at the zero mean, but in most of the cases your mean value can be there. Then you have to translate the variable so that zero mean can be there and you can easily go through the table to use it. But we are not using this thing. This is there when you are applying the thing in your early or other questions. But for just investigating the goodness of the fit, this is illustrated here. If we have a data with mean value, that mean value is represented in A by a straight line. This is your say this is your mean value. Your data is above or below the mean value. So if we plot that spread, calculate the standard deviation, it will take the shape of a curve, something like this. We will see that your spread is bigger. But if we use least square technique, still we have some error and residues. If we plot the residues, we will find that also follow standard deviation. That also follow normal distribution, but their spread is much lower than this thing. Okay, using these two parameters, actually some equations are there developed, and we can use that equation to measure the goodness of a fit. That is there in equation 17.10. R square value, it is called coefficient of determination. It depends on your ST, the error that is described here, calculated with respect to the average value. SR that we use there in our equation, using this ST and SR, we can calculate the R square value. If you have the experience of using Excel to find the trend line or curve fitting, that R square value, the Excel can easily calculate. The square root of R square value equal to R, it is called correlation coefficient. Have you heard about correlation earlier?
Yes, sir.
Yes, sir.
Correlation in signal processing is actually the thing that how two signals or two things are close to each other. To measure the closeness of the two things, we can use the correlation. Okay. If you have a random variable there, sometimes they can be correlated, or other cases they may not be correlated. For this reason, we use correlation. This is the simple equations to obtain the correlation coefficient for your straight line fit. Okay, you see that the equations that you used earlier, the terms, sum of x, sum of y, etc., can be used to calculate the value of R. And that value of R is your correlation coefficient. If you square this value, this is called coefficient of determination. That will explain how your model parameter can explain your observed values closely. Okay, if it is 1, that means your model fit, that 100% data that your model has can be explained with the help of that model parameter you determine. This is the important something. Apart from this linear regression, you may, apart from this thing, you may have some other scenarios there where your graph can be different. Okay, the one that we that I discussed for the case of VI characteristic of a diode, for example. If we have a VI characteristic of the diode for measured in the laboratory, we have seen that that characteristic can be just measured value can be something like this. Okay. You see that that will take the shape of an exponential curve, isn't it? Do you know what is the diode current? You know that diode current contain a value I0 e to the power, say, for example, some V divided by VT, something like this.
Yes, sir.
That's why with this, because many parameters are involved, that in this way, you see that, is it not that curve can be expressed in this generally in this way? For example, you can generally express this nature of the curve in this way. Y is equal to, say, alpha 1 into e to the power beta 1 x or something like this.
Yes, sir.
Here in this case, your y equal to I, your x equal to v, alpha can be I0 and beta equal to 1 by vt.
Yes, sir.
Fine. Then if this is the case, then can we apply the previously known thing, technique here to find
Yes,
the
sir.
value of alpha 1 and beta 1?
Yes, sir, we can.
We can, yes. Theoretically, yes, we can. Okay, but practically how it is complicated, let me explain to it, okay? If we want to go through it, our thing is what we have to calculate SR. SR is equal to sum of I equal to 1 to n. We have to calculate, for example, say yi minus y predicted, isn't it? In our case, y predicted will be equal to alpha 1 e to the power beta 1 into xi, isn't it?
Yes,
Yes,
sir.
sir.
We have to square it. You will see that now your SR is the function of alpha 1 and beta 1, is it?
Yes, sir.
Yes, sir.
Then like your previous case, we have to differentiate with SR with respect to alpha 1, set it equal to 0. Then we differentiate SR with the beta 1, set it equal to 0. Is it okay?
Yes, sir.
Yes, sir.
Now can you differentiate with respect to alpha 1 this equation? That will be equal to, like your previous case, minus 2 sum I equal to 1 to n. It will be equal to yi minus alpha 1 e to the power beta 1 xi multiplied by e to the power beta 1 into xi, isn't it?
Yes, sir.
Is this is clear to everyone?
Yes, sir.
Because you
Sir,
have to differentiate this factor.
Yes, sir.
sir,
That is
if
equal
we
to minus e to the power, if we differentiate this factor with respect to yi minus alpha into e to the power beta 1 xi with respect to what? The alpha I, isn't it? Would be equal to what? Minus alpha minus e to the power beta 1 into xi, isn't it?
Yes, sir.
Yes, sir.
And that minus is coming here, okay?
Yes.
And for your second case, it will be equal to 2 sum I equal to 1 to alpha. It would be equal to yi minus alpha into e to the power beta 1 xi multiplied by
Beta
X.
1.
X1 e to the power beta 1 x.
alpha 1 will go where? That is it alpha 1
Yes, yes, yes.
into beta 1 e to the
1.
power
Beta 1
beta
xi.
1 into xi, isn't it?
Yes,
Yes.
sir.
Okay. Can you solve this equation so easily?
No, sir.
What
No,
you
sir.
can have, what you have done earlier? Is it
Yes, sir.
possible so easily?
No,
I
sir.
would not say that it will be impossible, but it is not possible so easily. Okay. You need some high standard technique to solve this nonlinear type equations. Okay. You can use a Gauss-Seidel method, or you have to use some other iterative method to solve for alpha 1 and beta 1. Or you can use, for example, an algorithm present there. We call it optimization. We did not talk about it yet, but if you have your idea, then you can search for it. Okay. You have our SR. That SR is the function of alpha 1 and beta 1. And it is equal to sum I equal to 1 to n yi minus alpha 1 e to the power beta 1 xi squared. This is a function actually. What you can do in your MATLAB, we have a built-in function is called fmin search. Fmin search. Okay, you can define, you can set your data set there. You can define a function like this. Then you invoke this function here with some initial value. Then it can automatically give you the value of alpha and beta for optimal cases. Okay. But I think at this stage, it may not be difficult. It will be difficult for you to use it. But after a few days, inshallah, I will try to give you some idea about it. Okay. But another useful thing is that instead of going to that complexity, what you can do, you can make a change of variable so that your equation will resembles to a linear fit. Like y equal to say alpha 1 e to the power beta 1x. If we take logarithm in both sides, natural logarithm, that y1 equal to ln alpha plus beta 1 into ln x, isn't it?
Yes, sir.
Yes, sir.
If it is yes, then let us change the variable. Okay, we call it say capital Y is equal to say this is your A0. We can call it say beta 1 into x. Can we call it?
Yes, sir.
Yes, sir.
Now, if you originally what you will have happen, your x1 and y1 data will be given to you, isn't it?
Yes,
Yes, sir.
sir.
From your x1 and y1, your next step is what?
Finding ln y and
Finding out.
ln x.
That means you have to calculate. You have to
capital 1, capital X.
Yes. That means initially you will have this table with you. One is your X, another is your Y, isn't it? From that table, now you have to calculate your capital X and capital Y, isn't it?
Yes, sir.
Now you forget this region for the time being. Using this thing, you apply the straight line curve fitting regression technique that we used earlier to find the coefficient A0 and beta 1. Beta 1 can directly be used there. And if your A0 is available, you see that your A0 equal to what? Log
1 alpha.
alpha 1. So you can easily calculate the alpha 1. In this way, you can proceed, isn't it? Isn't it very interesting?
Yes, sir.
Yes, sir.
But not always this could be possible. If you have this thing with you, very similar, simple example, then you can do that. Like, okay, this is one example. Another example can be y equal to say alpha 2 x to the power beta 2. It is also a power fit, okay? We can also convert this thing in by using log. Log y is equal to log alpha 2 plus beta 2 into log x, isn't it?
Yes, sir.
In the same way, we can use this transformation and apply your straight line technique there, and we can proceed with finding the value of alpha or alpha. We may have some equation called saturation equation. Y is equal to say alpha 3 into x divided by beta 3 plus x. This type of equation has this nature, okay? Say at x equal to 0, it will have value equal to 0. As you see that as your x value is increasing, then what will be the limiting value of x, value of y for higher value of x? Can you find it? Say your y is, say your x is tending to infinity. What is the value of y? You can easily apply your L'Hospital's rule there to find the value of y. Limit x tends to infinity, then you differentiate your upper one and differentiate your lower one. Is it not equal to something like this? Equal to alpha 3 divided by beta 3. Is it okay? Hey, what is the value of your y as your y is tending to x is tending to infinity?
Sir, is it alpha 2?
Hey, don't you know your L'Hospital's rule in your limiting algebra? Have you heard about this rule earlier in your intermediate level or something like this?
Yes, sir.
Yes, sir.
So what is that rule? What is the utility of this rule?
Sir, if the ratio is like 0 by 0 or infinity by infinity, then we can simply
But
differentiate.
then if we just make your x tends to infinity, is it not the case that it becomes infinity by infinity?
Yes, sir.
Then in this case, what you need to do, you have to differentiate
We
your
can
numerator
differentiate.
and differentiate your denominator and apply the rule.
Yes, sir.
If we differentiate our numerator, it is simply alpha 3. And if we differentiate your numerator, it is equal to 0.
Beta 3. Oh, sorry,
It
sir.
is equal to 1 actually. So then this value would be equal to alpha 3 actually. Is it okay?
Yes, sir.
Then if you want to, then you can easily plot this for higher value of x, it will be equal to alpha 3. So your maximum value is alpha 3. It is simply going in this way. Is it? It is a saturating curve. Have you find this type of curve in your experiment in electrical machine? Is it not have you heard about BH curve in your first year or even in your second
sir.
year or third year?
Yes, sir.
Is it not your BH curve is something like this?
Yes, sir.
It is increasing and gradually getting saturated for higher values of the
Saturation
flux will not increase if you matter of contain magnetic element or iron or something like this, ferromagnetic element. This type of curve is called actually a logistic saturation curve. And general name of this equation is the Froelich equation, okay? Then usually,
Sir, what equation can you repeat?
sorry?
Sir, what equation can you repeat? I missed the word, sir.
Spelling may be incorrect.
Okay, sir. Frolic equation.
In earlier days, in most of the cases, to fit a BH curve, your Frolic equation is generally used. Okay. That's why you see that your equation is y equal to what? Y equal to alpha 3 into x divided by beta 3 plus x. You have to find your alpha 3 and beta 3 that you cannot find so easily. What you can do, you can write this equation in this form. Y is equal to beta 3 plus x divided by alpha 3x. Can you do that? And then it will be equal to 1y is equal to what? Beta 3 divided by alpha 3 into 1 by x plus 1 divided by alpha 3, isn't it? Then you call this quantity capital Y and this quantity X. Then your equation will be equal to Y is equal to 1 divided by alpha 3 plus beta 3 divided by alpha 3 into X. This is a constant, call it A1. This is another constant, call it A0. Then your equation would be equal to Y equal to A0 plus A1 X, isn't it?
Yes, sir.
And you can easily use this equation to fit, okay? So with this thing, I want to finish my lecture for today. We took around 15 minutes at the beginning, but be careful about your engagement, okay?
Sir,
Yeah.
sir,